In this video, I want to talk about the wave equations that go with sinusoidal waves. Now, we have a picture here where I've tried to draw what we picture an electromagnetic wave looking like. In this case, we've got a wave that's traveling in the positive x direction. Its electric field is oscillating parallel to the y-axis. It's oscillating up and down in that xy plane. The magnetic field is oscillating parallel to the z-axis, so picture that as in and out of this screen, and it lies completely in the xz plane. Notice that at this first point right here, where at this red dot, that the electric field and the magnetic field are both maximums at the same time. And here you can see at this dot, they're both minimums at the same time. Now, way back when we studied mechanical waves, we came up with a description to describe the amplitude of a mechanical wave traveling in the positive x direction. We said its amplitude, which was going to be y, or its displacement from equilibrium, that's really the correct word, its displacement from equilibrium depends on two things, its position and its time, and it's equal to a sine omega t minus kx. It's a function of position and time, because if I pick a particular point on the graph, like this red dot, at this moment in time, it's at the electric field and magnetic fields are at max. But if I were to wait in a few seconds or a fraction of a second, it would actually have an electric field and a magnetic field of 0 at this point. At the same time, this first red dot is at a maximum. This second red dot is at a minimum. But there again, if we waited till a different time, it could have a maximum. So the size of the wave at any point depends not only on what time it is, but its location. Omega is called the angular frequency. And it is equal to 2 pi times the frequency. It has units of radians per second. K is called the wave number. And the wave number is equal to 2 pi divided by the wavelength. So it has units of radians per meter. A, of course, is amplitude. When we talked about mechanical waves, the amplitude would have been measured in meters. But in this case, it's not going to actually be a physical amplitude. It's going to be the size of the electric field if we're writing an equation for the electric field. And so it will have units of either volts per meter or newtons per coulomb. If we're writing the equation for the magnetic field, it would have units of Teslas. So what we really get is we get two new equations. We get one for electric fields. I'll write it in blue just to be kind of consistent. The electric field as a function of x and time is equal to the maximum value of the electric field. That's what we think of as an amplitude, whatever that maximum value is, sine omega t minus kx. And the magnetic field strength is given by B max times sine omega t minus kx. Remember, we already have a very good relationship between E max and B max. E max is always just C times B max. So if we know either one of those, we always know the other. Another interesting relationship that we can get just by looking at the wave number and the angular frequency, if we look at omega divided by k, Omega is 2 pi f. K is 2 pi over lambda. But you'll recall from your middle school days that if you divide by a fraction, that is like multiplying by the reciprocal. And of course, the 2 pi's are going to cancel. This just equals f lambda. Hopefully you remember that that is the wave velocity. The velocity of a wave is f lambda. So we can also say the velocity of the wave is the angular frequency divided by the wave number. That just comes in handy sometimes. Just a fun relationship. Let's look at an example. I will point out that the equations that we have here, if we make it travel in the negative x direction, we have to make these pluses. If we travel in the z direction, we have to make it z's. So when you're doing a problem, and I know there's a problem in the homework where the wave is not traveling in the positive x direction. So for wave, I'm not going to rewrite both of them, but I'll rewrite traveling in the negative x direction. This equation is going to just change by one little sign. If it's traveling in the positive z direction, we change that x to a z. So if it's going in a positive x, y, or z, this is going to be a minus sign. If it's going in a negative x, y, or z, that's going to become a plus sign. Just want you to be able to think about it so we don't miss any signs in the problem. So here's an example. We have a carbon dioxide laser, CO2 laser, emits a wave that travels in the negative x direction. So we're going in that negative direction. We want to think about what that looks like before we put any numbers on it. If the wave is traveling this way, there's our velocity. When the electric field is pointing straight up, that's the positive y direction. Let's think about what's happening if that's the direction of the electric field. We need to be able to put our thumb in the direction of V, our fingers in the direction of the electric field, and curl our fingers towards B. We can see our magnetic field in this case would point in the negative Z. That's our magnetic field. Now, a few seconds later, when the electric field is pointing down, the magnetic field will be pointing in the positive Z direction. Again, if you check, you can see that if your thumb points to the right and you hold your hands and your fingers are straight down, when you curl your fingers, B would come out of the board. Now, they didn't tell me that E was in that direction. I just wanted to practice that right-hand rule. I can change that. Let's put E in a different direction, because it's certainly possible. We know that E has to be either along the y-axis or along the z-axis, because it has to be perpendicular to this negative x-axis. So let's let B this time point in the positive z. If B is pointing in the positive z-axis, There, I'm sorry, E. There's my electric field. With my thumb, I just have to think about it. I have to rearrange my hand. When I curl those fingers, I can see that B is going to be up. Takes a little time to figure out how to hold your hand, but you can see it. So I don't really know how E and B, whether E's along the Z-axis or E's along the Y-axis, but I want to be able to practice that right-hand rule. It doesn't matter to solve the rest of the problem. Let's go on with the rest of the problem. They tell us that this carbon dioxide laser has a wavelength. Whoops, let's go back to black. We have a wavelength of 10.6 micrometers or micrometers, and we have a maximum electric field of 1.50 megavolts per meter. We want to be able to write all of the equations for this wave. All right, think about the formula. E equals E max, well I know E max, sine omega t plus kx, because we're going in the negative direction, that's going to be a plus. They don't tell me the frequency, but if I know the wavelength, I know frequency, because I know for an electromagnetic wave that V equals lambda F, and V is just the speed of light. Lambda is 10.6 times 10 to the negative 6 meters. And that will give me F. This is meters per second. If I do the math there and I do 3 times 10 to the 8 divided by 10.6 times 10 to the negative 6, I get that the frequency F is 2.83 times 10 to the 13th, but I want omega. So omega is 2 pi times F. So if I multiply my answer by 2 pi, I get that my angular frequency is 1.78 times 10 to the 14th meters per second. I think we're in the infrared range because our frequency is a little too low for visible light. Visible light is going to be on the order of 10 to the 14th. So there's omega. K is 2 pi over the wavelength. So I'm going to say 2 pi. And I'm going to divide it by that 10.6 times 10 to the negative 6. And that is 5.93 times 10 to the 5th. And I wrote median. That's supposed to be radians. I'm so sorry. Let me get my units right. I don't know why I put meters per second. Omega is going to be radians per second, and K is going to be radians per meter. Okay, so what's our equation? E equals E max, which is 1.50 megavolts. If I want to leave it in megavolts, I can. If I want to say times 10 to the 6, that's megavolts per meter. Sine, and here it gets a little messy. omega is 1.78 times 10 to the 14th times t, and then plus k is 5.93 times 10 to the 5th times x. And it might be, since we have an x in our formula, we might prefer not to put those x's in the middle. I don't want that to confuse you. I could put a multiplication dot, 1.78 times 10 to the 14th, 5.93 times 10 to the 15th, 10 to the 5th, not 15. Changing my numbers, I'm not allowed to do that. So 10 to the 5th. That's the one that's it. We've got it. If I want to know the magnetic field, I have to take E max and multiply it times and divide it by C. So B max is E max divided by C. So 1.50 times 10 to the 6th divided by 3 times 10 to the 8th. And I get really a pretty simple answer. I can write it in scientific notation, or I can write it out either way. It's 5 times 10 to the negative 3 Tesla. And then sine. The rest of this is identical. 7.8 times 10 to the 14th t plus 5.93 times 10 to the 5th x. Let's do one more of these. This is all I want to talk about in this particular lesson. So let's look. I don't want to do everything. I want to save some for our live lecture, but I'd like to do maybe one problem out of the back that at least examines this. Let's maybe look at problem 8, I guess. I'm debating whether I want to do 7 or 8. I'll tell you what, let's look at 7 and we'll save 8 for class. If we look at number 7 out of the back of the chapter, it tells us that the electric field of a sinusoidal electromagnetic wave obeys this equation. E equals negative 375 volts per meter, so that's my electric field. Sine gets a little messy here. 5.97 times 10 to the 15th. Radians per second times t. So there's my omega t plus 1.99 times 10 to the 7th radians per meter times x. So you can see this is my omega t plus k x. You just have to look and pull things out of the equation. It says, what are the amplitudes of the electric and magnetic fields of this wave? Well, the electric field amplitude, and we'll go with just its absolute size, is 375 volts per meter. All the negative means is that it was pointing in the negative direction at that moment. The magnitude of B is going to be that number divided by 3 times 10 to the 8th meters per second. It's not obvious that that comes out in Tesla, but if you play around with the units, you see that it does. 375 divided by 3 times 10 to the 8th. And I get that the magnetic field is 1.25 times 10 to the negative 6 Tesla. Or you could say 1.25 microtesla. So that's the answer to part A. They like my answer in the back of the book. I'm a big believer in checking your work. B says, what are the frequency, wavelength, and period? Frequency, wavelength, and period. Well, we know that omega is 2 pi f. So f is 2 pi, is omega divided by 2 pi. So omega is 5.97 times 10 to the 15th divided by 2 pi. Now when you divide by 2 pi, make sure you put a parentheses around that 2 pi, or whatever you need to do to be sure you're dividing by 2 and by pi. It comes out to be 9.50 times 10 to the 14th hertz. The wavelength, I believe, was the next thing they asked for. What is it? Let's see. What is the frequency, wavelength, and period? The wavelength, lambda, is equal to, well, let's just look at our formula for our number. We know our wave number, K, is 2 pi over lambda. Tells me lambda is equal to 2 pi over K. So 2 pi divided by 5.93 times 10 to the 5th. And my wavelength came out to be 1.06 times 10 to the negative 5 meters. If I want to make this into micrometers, I can. If I make this number 10 times smaller, then I make this number 10 times bigger. So this would be equivalent to 10.6 micrometers. That's what we actually had on the previous problem for our wavelength. It didn't ask us to do it that way. There's certainly nothing wrong with just leaving it like this. The period, I believe, was the next thing. And we know that period is simply the reciprocal of the frequency. So if I do 1 divided by 9.50 times 10 to the 14th power, I get a period that's 1.05 times 10 to the negative 15 seconds. So a very, very short period. Uh-oh. I got the right frequency and I've got the right period, but I have the wrong wavelength. So let me see if I typed something in wrong or I copied a number wrong. Oh, I copied a wrong number. I'm so sorry. I took the number from up here instead of the number from right here. Let me fix that very quickly. I'm sorry, I probably caused some confusion, but I don't want to go back and start over. For this problem, our k was 1.99 times 10 to the 7th. So let's try that again. If I do 2 pi divided by 1.99 times 10 to the 7th, I get different value. We fix that. No wonder we got the same answer we got above, as I used the same wave number from the previous problem. That explains that. This actually came out to be 3.16 times 10 to the negative 7. I'm glad I checked. This is also 316 nanometers. We often do visible light in nanometers. This isn't visible though. This is going to be in the infrared. It's a little, I'm sorry, this is going to be in the ultraviolet. That wavelength is a little too short. This is UV radiation. We can only see to maybe 400 nanometers. Anything shorter, we're not going to see it. How do I know that? If I change this to 10 to the negative 9, that is 100 times smaller, so this has to be 100 times bigger. So it's 316 nanometers. Is this visible to humans? It is not. It is, humans can only see 400 to 700 or so. And then the last question says, what is the speed of the wave? Well, it's an electromagnetic wave. So its speed better be, this is what I hope I'm going to get. But we said, you know, you can check it. It should be the ratio of omega over k. And those were the two numbers they gave us. They said in the original that omega was 5.97 times 10 to the 15th. And that was what? Radians per second. And that k was 1.99 times 10 to the 7th. That's radians per meter. The radians, of course, go away. We end up with meters per second. 5.97 times 10 to the 15th divided by 1.99 times 10 to the 7th. Oh, what do you know? It came out to be exactly 3 times 10 to the 8th meters per second, just like we predicted. That should be true. That's a nice check for a wave equation. If it's an electromagnetic wave, that speed should be 3 times 10 to the 8th. All right, I'm going to stop here. Hopefully that was helpful to you.